So we're now going to define what we mean by convergence of a series. Suppose we have this infinite series, which is a0 plus a1 plus a2 plus dot dot dot. We define the nth partial sum using the notation Sn in the following way. S0 is a zeroth partial sum, and it is a0. S1 is the sum of a0 plus a1. S2 is the sum of a0 and a1 and a2. S3 is a0 plus a1 plus a2 plus a3. Now, if you recall the previous examples, we observed the values of S0, S1, S2, S3, and the idea is to see what is happening to Sn, which in this case is A0 plus A1 plus A2 plus dot dot dot, and this is An. And this can be written in sigma notation, k going from 0 to n of an. And when you observe these numbers, and as n gets larger and larger, if these numbers here approach a particular value, then we say that this infinite series has a finite sum, and that sum is, and if it has a finite sum, we say it converges. So let's put this in words. If the sequence, so this is a sequence of partial sums, Sn, it has a limit, that is, if the limit as n approaches infinity of Sn is equal to S, where S is some real number, then we say the series, this infinite series going from n equals to 0 to infinity of an, converges. And we say the sum is equal to S. So we write this all down. The limit as n approaches infinity of Sn is the sum to infinity of the series, and this is equal to S. So this is what we mean by the sum of an infinite series. It means the limit of the sequence of partial sums. So in this example, we have a simple series and a simple question. Does this series converge or diverge? For a start, it will be useful to write down what this series is. So n equals to 0 to infinity of minus 1 to the power of n, which is equal to minus 1 to the power of 0 plus minus 1 to the power of 1 plus minus 1 to the power of 2 plus minus 1 to the power of 3 plus dot dot dot. And if you simplify each of these terms, you will get 1 plus minus 1 plus 1 plus minus 1 plus dot dot dot. Now, when you look at this series, it may be tempting to sum the series in the following way. 1 plus or minus 1 is 0. 1 plus or minus 1 is 0. 1 plus or minus 1 is 0. And therefore, you might be tempted to think that this infinite series has a sum which is equal to 0. However, you have to be very careful to remember that this is an infinite series, and all the algebraic processes that work for finite series may not necessarily apply to infinite series. In particular, this is not how you sum an infinite series. We need to go back to the definition of an infinite series, and in order to determine whether an infinite series converges or diverges, we need to consider the sequence of partial sums. So let's do that here. So here, the 0th partial sum is equal to minus 1 to the power of 0, and that's equal to 1. The first partial sum is equal to minus 1 to the power of 0 plus minus 1 to the power of 1, which is equal to 0. The second partial sum is minus 1 to the power of 0 plus minus 1 to the power of 1 plus minus 1 to the power of 2, which is back to 1. And the third partial sum you can work out yourself is equal to 0. And you can see that there is a pattern here. If you're interested in the nth partial sum, by observing the earlier pattern, you will be able to see that the 0th partial sum, the second partial sum, the fourth partial sum are all equal to 1. So when n is even and when n is odd, you have a partial sum which is equal to 0. So 0 when n is odd. So whether or not this series converges or diverges depends on whether the nth partial sum depends on what the value, on what the limit of the nth partial sum is as n approaches infinity. And since Sn is defined as follows, we would say that this limit does not exist because Sn oscillates between 0 and 1. Therefore, the sum of this series here, minus 1 to the power of n, does not exist, or we say it diverges because Sn, the nth partial sum, does not have a limit. In this example, we are going to work out whether this series here converges or diverges. Let's begin by listing a few terms in the series so we have a better idea of what the series looks like. So when n is equal to 0, you have 1 over 1 times 2. When n is equal to 1, you have 1 over 2 times 3. When n is equal to 2, you have 1 over 3 times 4 plus dot, dot, dot. Now, in order to understand this series better, we're going to rewrite 1 over n plus 1 times n plus 2 in a slightly different way. And this different way is as follows. You can write the reciprocal of n plus 1 times n plus 2 as 1 over n plus 1 take away 1 over n plus 2. Now, where this came from is the stuff of partial fractions, which you will understand a little bit more when you complete the module on integration. For now, let's just verify that this result is true. So we're going to work out the right-hand side and verify that it in fact is equal to the left-hand side. So 1 over n plus 1 take away 1 over n plus 2. When you bring things under a common denominator, is n plus 1 times n plus 2, and this is n plus 2 take away n plus 1, which is equal to n plus 2 minus n minus 1 over n plus 1 times n plus 2, which then gives you 1 over n plus 1 times n plus 2. So indeed, we have verified that this expression here can be decomposed into two simpler fractions. Right, we're going to make use of this relationship or this equation to rewrite the series in the following way. So sigma n from 0 to infinity of 1 over n plus 1 times n plus 2 can be alternatively written as sigma from n equals to 0 to infinity of 1 over n plus 1 take away 1 over n plus 2. And what we're going to do in the next slide is we're going to generate the partial sums for this series, and the partial sums will tell us whether this series has a finite sum or not. Okay, so let's recall what we've got so far. We've got sigma n from 0 to infinity of 1 over n plus 1 take away 1 over n plus 2. And we're supposed to work out whether the series converges or diverges. So let's start with the 0th partial sum, which is equal to 1 over 1 take away 1 over 2. And this is equal to half. Then we generate our first partial sum, which is 1 over 1 take away 1 over 2 plus, and there is another term here, 1 over 2 take away 1 over 3. And when you evaluate the first partial sum and open up the brackets, you will notice that minus half cancels with a half, and the sum is 1 take away a third. Next up, we have the second partial sum, which is equal to 1 over 1 take away 1 over 2 plus 1 over 2 take away 1 over 3 plus, and when n is equal to 2, you get 1 over 3 take away 1 over 4. When you sum the terms in your partial sum, you will notice when you open up the brackets, minus half cancels with half, minus a third cancels with a third, and you are left with a simple expression, which is 1 take away a quarter. So you have one number left at the start and one number left at the end. Now, if you continue this process and write down what the nth partial sum is, you will have 1 over 1 take away 1 over 2 plus 1 over 2 take away 1 over 3 plus 1 over 3 take away 1 over 4 plus ... and then you have 1 over, the last term is n plus 1 take away 1 over n plus 2. Now, if you open up the brackets for this sum, you will notice that all the terms, minus half will cancel with half, minus a third will cancel with a third, and this guy here, 1 over n plus 1, will cancel with something in an earlier bracket. So all of the intermediate terms, or all the terms in between the first and the last term, will cancel out, and in the end you are left with one term at the start and one term at the end. So here it appears like you've got a really nice formula for the sum to n terms, for the nth partial sum, and that is equal to 1 minus 1 over n plus 2. So what does it mean if a series converges? Well, we look for the limit as n approaches infinity of this partial sum, of the nth partial sum. And since we have a really nice formula, this limit can be easily found by writing Sn equals to 1 minus 1 over n plus 2. And this is an easy limit. As n approaches infinity, this guy approaches 0, so this limit is equal to 1. So what you are saying is that, going back to the series, let's draw a line down the middle here. Box this up so we can continue the problem here. So what you are saying here is that since the limit of Sn is equal to 1, it means that sigma n from 0 to infinity of 1 over n plus 1 take away 1 over n plus 2 converges, and it converges to 1. So that is, going back to the original problem, sigma n going from 0 to infinity of 1 over n plus 1 times n plus 2 converges, and the sum is equal to 1. This series here is called an example of what we call a telescoping series. And it's called telescoping because you have a series here which shrinks down to just the first term and the last term.